Hi everyone, thank you all for being here and thank you for the organizers for giving me the chance to share my research with you today. I'm Gregory Kasteratos, a PhD candidate in informatics at Ionian University. My work focuses on drone path planning optimization. This presentation explores the optimization of drone paths through strategic launchpad positioning, a critical but often overlooked aspect of UAV operations. Path planning in drones is an essential aspect in UAV operations, ensuring the drone flies efficiently while meeting the mission requirements. Applications range from disaster relief and agricultural monitoring to logistics and surveillance, where effective path planning directly contributes to operational success by optimizing resource utilization, such as battery, lifetime, and time. Path planning is critical because UAVs have limited resources such as battery life and payload capacity. Inefficient routes can lead to incomplete missions or increased operational costs. On the other hand, effective path planning directly impacts the mission success, whether it's delivering medical supplies, monitoring crops, or conducting surveillance. By reducing energy consumption through smarter path planning, drones can extend their operational range and support longer missions, particularly in applications like surveillance and agriculture. In other words, path planning is a cornerstone of UAV operations, ensuring mission success and efficiency. This presentation explores how strategic launchpad positioning combined with advanced algorithms such as multiple traveling salesman problem MTSP and genetic algorithms GA can overcome existing limitations and optimize operations when dealing with multiple UAVs. More particularly, these are the key contributions. A. It presents the significant role of strategic launchpad positioning in enhancing the efficiency of drone path planning. And B. Introduces a timely solution for identifying a near optimal launchpad for a flight plan. We've heard so far the phrase launchpad positioning a couple of times, but what do we actually mean by this? Strategic launchpad positioning involves selecting the best starting location of UAV operations to minimize redundant travel distances and maximize mission efficiency. By placing the launchpad closer to clusters of mission critical locations, the overall distance traveled by drones is significantly reduced. Let's now have a look at an example. Assuming that we have 10 stations as shown in the top left hand corner and 3 drones, given any launchpad location, an MTSP algorithm would try and create a mission with 3 routes in a way so that the 3 drones fly the minimal distance. Changing the launchpad to a new location and running the MTSP algorithm again, it generates entirely different route configurations as we can see. Let's for example take this sample over here and place a launchpad over here. Running the MTSP algorithm, it would generate those 3 routes for the 3 drones. Now, changing the launchpad to a different location and keeping the same stations, as we can see, we haven't changed stations here, it generates a totally different plan altogether. Again, doing the same thing, we can see the same thing again on this example here. Again, we have the same stations, but all we've done is change the location of the starting point, and MTSP, as we can see, generates yet again 3 different routes. This flexibility in route optimization highlights a critical aspect of the MTSP algorithm. It continuously seeks to minimize the total travel distance by exploring alternative route structures. When the launchpad is repositioned, MTSP evaluates how the new location affects the travel distances between the sensor station and adjusts the routes accordingly. This is inherent to any MTSP implementation. What is the interesting bit here is the fact that repositioning the launchpad introduces an opportunity for the algorithm to explore different route combinations that may not have been considered optimal under the previous configuration. That leads to the question, How can one predict a launchpad location that the MTSP produces the most optimal flight path? In other words, where can I place the launchpads in the field so the drones fly the minimum distance? This is actually the subject of our research, and we will endeavor to explore methodologies for determining the most advantageous launchpad location for a specified flight plan. The methodology developed in this study must be validated against the ground truth to ensure measurable and reliable results. The initial step in this process is to establish the ground truth for the scenarios under consideration. This means that we need to determine a methodology that consistently identifies the optimal starting point for the area of interest, while temporarily disregarding the computational time required to achieve this outcome. The worst case scenario in terms of time complexity is the application of the brute force method, which involves evaluating every potential point in the area to determine the optimal starting point. Although this method is computationally expensive, it guarantees the identification of the best starting point. Let's have a look at an example. Consider the scenario shown here where sensor stations are distributed across a field, as we can see, with dimensions of 60 units in height and 1500 units in width. Here being the first point 00, the first location, and here being the last one 599,1499. The brute force approach would require running the MTSP algorithm 1500 times 600, that gives us 900,000 times to evaluate each point in the field, and from those pick that point that produces the smallest distance. As we can see, the number of times that needs to run is incredibly high. Despite the significant computational expense, this method is crucial as it ensures the determination of the optimal starting point, leading to the minimum total travel distance when the MTSP is applied. While this method ensures accuracy, its computational expense grows significantly with larger problem sizes, making it insufficient for large-scale applications. Therefore, it is essential to explore alternative methods that can provide optimal or near optimal solutions with a significantly lower computational cost. A promising approach to solve this problem efficiently is the use of genetic algorithms, also known as GAs. GAs are heuristic search methods inspired by natural selection and the principles of evolution, which have been successfully applied to a wide variety of combinatorial optimization problems. The central advantage of GAs is the ability to explore large and complex solution spaces without exhaustively evaluating every possible solution, making them computationally feasible even for problems with large number of potential solutions. The evaluation results. A total of 80 representative flight plans, each corresponding to a unique scenario, were developed. These scenarios varied in the number of stations, which were set at 5, 10 all the way to 100, and incorporated between 1 and 10 drones. Each flight plan was repeated 9 additional times for a total of 10 iterations per scenario to account for the stochastic nature of the random station locations. Consequently, the study included a total of 80 scenarios times 10 iterations, resulted in 800 tests, each executed twice, once using brute force to determine the optimal launchpad, and then again using the GA so we can compare the two. For each time, measurements were recorded for both the brute force and GA approaches, specifically focusing on the total distance traveled and the time required to identify the optimal starting point. The results. In order to test the effectiveness and efficiency of the proposed methodology, this work utilizes the following two metrics. A. The performance achieved of the GA approach as a percentage in relation to the ground truth provided by brute force, and B. The time ratio of the GA approach in relation to the ground truth provided by brute force. The performance achieved is calculated using equation 1 over here and shows how close GA reached the exact solution provided by brute force. Accordingly, time ratio is calculated using equation 2, whereby values close to 0 indicate the superiority of GA. Values close to 1 indicate the equivalence of GA to brute force, while values greater than 1 show the superiority of brute force over GA. The x-axis for both graphs shows how many ground stations, sensor stations, are used in each scenario. Based on the result obtained, as shown in the graphs, the GA achieves accuracy comparable to brute force while requiring significantly less computational time. More specifically, on the other hand side graph, we see that the total travel distance generated when GA is used to predict a starting point is near match of that of the brute force, ranging from 97% to 100%. Additionally, looking on the right hand side graph, the computational cost of the genetic algorithm is significantly lower than that of the brute force method, with time ratio of GA over brute force methods being in the range of 0.004490 to 0.0091891, indicating thus the clear superiority of GA approach as previously mentioned. Concluding our experimentation, we have to note that while the brute force method guarantees the exact optimal solution, its computational cost becomes prohibitive for large-scale problems. In contrast, the genetic algorithm A provides a near optimal solution with accuracy levels exceeding 97%, and B drastically reduces computational time, achieving results up to 4 orders of magnitude faster than brute force. This balance of accuracy and efficiency makes the GA an ideal choice for large-scale sensor network optimization problems, where near-time or near real-time decision-making is crucial. Conclusions. This study has demonstrated the significant role of strategic launchpad positioning in enhancing the efficiency of drone path planning. By utilizing the MTSP algorithm, we show that repositioning the launchpad can lead to substantial reduction in redundant travel distances, ultimately improving overall mission performance. These findings underscore the critical importance of adaptive deployment strategies in the design of energy-aware drone systems. Future research will focus on fine-tuning the internal parameters of the genetic algorithm to enhance its performance. Additionally, exploring alternative methods for predicting the optimal starting point will be pursued to further improve the overall results. Last but not least, this research was supported by the European Union's remarkable project. Thank you for your attention. We welcome any questions or feedback to further discuss and refine the presented concepts. Please do so by emailing us using this address, gkestratos@ionio.gr.